Hello friends, welcome to the channel. So here let's look at today's daily challenge problem. Maximum candies allocated to key children. So here we are going to use binary search. So I don't want to go through all the statement of the problem. But here there are several points I want to emphasize. First, you can divide each pile into any number of subpiles, but you cannot merge two piles. This is the one assumption. Another assumption is that each children can be allocated candies from only one pile of candies, and some piles of the candies may not go unused, right? So this is the two main assumptions. Another one is that we want to return the maximum number of candies each children can get, right? So for this one, it's 3, right? You can allocate each each child 5, right? For this one, you have 11 children. You have only 2 piles. It's impossible to do the job. So here, the length of the candies can be as long as 10 to the power 5, and so k can be also very large. Therefore, you need to think of time complexity. So with that said, we are ready to explain our method. So here we are going to check, right? Check given a key, right? So if given a number, let's say n candies, so if we want to assign each case n candies, can we assign all the key children this number of candies, right? So basically, we want to check, right, the summation of candies over n integer division in candies for y in candies, right? If this number is larger than the greater than or equal to k, then we can allocate, right? Otherwise not. And however, we cannot check for all the possible candies, because if k is very large like this, it's impossible. Or if this candy this range is very large, it's impossible you check, say, from 1 to 10 to the power 7, right? So this actually exactly the point where binary search come into play. So here we are going to do 2 things. First is to define a Boolean function to produce order. This is the one thing. And then once we can produce order, so then we can do search space shrinkage. Shrinkage. So this is our plan, and in between we are going to coding and explain the logic. So now let me first write down the function called can allocate, right? So if we want to assign, say, n candies, right? So can we finish that? So basically it's just a sum, right? Return if sum of this y over n candies, right, for y in candies. So if this one is greater than or equal to k, right? So this is just one version. I'm going to maybe later expand a little bit, but this, if you write like this is just one line. And then you are going to do binary search. So when you do binary search, you need to have a search space. So here the low and the high, the low will be 0. At most you can do this, right? Candies, because you cannot separate you can separate piles, but you cannot merge piles. So this is the maximum. So our goal is to find max in candies such that can allocate in candies is true, right? So here, because we are finding max, I want to shrinkage from above to below. So here, basically, well, L is less than low is less than high. So what we're going to do, mid will be this: high minus low, integer division by 2. Then we are going to check if not, can allocate mid. So in other words, your number is too large. You cannot assign those. So we're going to set high equals made -1, right? So otherwise, if you can allocate, and then you're going to set low to be the mid, right? So then in this way, I'm going to return the high, right? So this is the full code for this problem. Let me first test it and then do a comment. Yeah, it passes the 2 test cases. So now let's look at the generic case. Yeah, it passes the generic cases. So this is the one way of writing the code. It's very short, right? It just writes this function as one line, and then you do this determines the search space, and this do the search space shrinkage, and then you do the return. So actually, sometimes if you use binary search, it can be tricky. Like here, what should you write? Less than or equal to. So this is one. And here I'm shrinking from above to below. And sometimes for some problem, like say find min, so you can also consider, or you should consider from lower to up. Basically change this one to be L plus the half of this search space range. So basically you need to do this according to the specific problem logic, right? And then the return, sometimes you need to return L, sometimes you need to return H, the high part, and sometimes you can return both because they are coincide. But you need also to digest and grasp the main idea. So this is the one. Another thing is that here I'm using the comprehension essentially, but you can also expand this function a little bit. So here let me do this and write another version. So for clarity, let me copy this one, and then so I'm going to search this one to be change the one to be version v1, and then I'm going to expand a little bit. So here can assign. So let's see the number of children, right? And children. So we can assign to those number of children, and then we just need to make sure if we can get this one greater than or equal to k, then we can just stop, right? So basically, for y in candies, right? In children, increment is y integer division by n candies, right? And then if in children is greater than or equal to k, already achieved, then just return true. And otherwise, if after this for loop nothing has returned, then you're going to return false. So this also works, but it's a little bit longer than this one-liner. So let's check that. Yeah, it passes the 2 test cases. Now let's look at the generic case. Yeah, it passes all the cases. So with this comment finished, I guess that's basically about it for the current problem. If you want to practice more about binary search and their applications in different scenarios or problem settings, so you're welcome to use our binary search playlist and do more practice. Thank you for